Hello everyone, welcome to physics class. This is the fourth lecture on the chapter electrostatic potential and capacitance. Till now, we have focused on the concept of electrostatic potential and also we have seen what is equipotential surface. Today's class, we are going to discuss the next topic, that is electrostatic potential energy. So let us begin. We already know the definition of electrostatic potential energy. We have seen that electrostatic potential energy of a charge q at a point in an electric field is the amount of work done by the external force in bringing the charge q from infinity to that point. So mathematically we can write the potential energy at a point as W infinity P, which is given by UP minus U infinity. Since U infinity is equal to 0, this can be written as UP. That means potential energy at the point P is W infinity, that is work done to bring a charge from infinity to the point P. Also we know, let us find out the relationship between electrostatic potential and electrostatic potential energy. From the definition of electrostatic potential, it is nothing but the work done from infinity to the point P per charge, unit work done per charge. So you can write work done per charge W infinity P divided by Q as equal to Vp, or you can write W infinity P is equal to Q into Vp. Now compare these two equations. From the first equation, W infinity P is equal to UP. From the second equation, W infinity P is equal to Q into Vp. So we can write UP is equal to Q into V, or U is equal to Q into V. This is the relationship between electrostatic potential energy and electrostatic potential. So electrostatic potential energy is the product of charge times the potential at that point. Now let us find out the electrostatic potential energy of some charge configurations. First we will take the simple case, that is electrostatic potential energy of a two charge system. So let us imagine a coordinate system x, y, z and the origin be O. Now we have to bring two charges, or we have to assemble two charges at point A and point B. So we are bringing charge q1 from infinity to the point A. Similarly, we are bringing the charge q2 from infinity to point B, so that we have the system q1, q2. For that, let us take the distance from origin to the point A as r1, or the position vector of point A is r1 vector. Similarly, position vector of B is r2 vector. Let the distance between the points A and B be represented by r12. Now, let us find out. We will do step by step. First, we will bring the charge q1 to the point A from infinity to the point. Then after that, we will bring the charge q2 to point B. In order to bring the charge q1 from infinity to point A, we need not do any work. Why? Because there is no electrostatic repulsion, or there is no electric charge there at origin or anywhere. So there is no potential there. So no need of any work. So work done in carrying charge q1 from infinity to A can be written as W is equal to 0. Next step, we have to bring the charge q2 to the point B. But at point B, there is a potential, because due to the presence of charge q1 at point A. We know that the potential at point B due to charge q1, we can write it as VA, that can be written as V is equal to 1 by 4 pi epsilon naught q1 divided by R. We know how to calculate. Since there is a potential, so there is a potential energy associated with this q2 now. In order to calculate the potential energy, you know the relationship between potential and potential energy. Since the potential is given, whatever charge you are bringing, you have to multiply by the potential, you will get the potential energy. So while bringing the charge to the point B, the potential energy, or the work done in carrying charge q2 from infinity to B, can be written as q into q2 into V, or potential at point B into charge. Charge is q2 here. So you can write it as V into q2, or we can write it as 1 by 4 pi epsilon naught q1 q2 by r12. This is the work potential energy of the charge q2 at point B. Now if we calculate the total work done, we will get the total potential energy. In case of the first step, that is to bring charge q1 from infinity to B, the work done is 0. To bring the charge q2 from infinity to B, the work done is 1 by 4 pi epsilon naught q1 q2. by R12. So you have to add the first work done and the second work done. Since the first work done is 0, the total work done will be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12, and this will be the potential energy of this system. So you can write U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. This is the electrostatic potential energy of a two charge system. Next, we will calculate the electrostatic potential energy of a three charge system. So first we will consider a coordinate system, a origin, and three charges Q1, Q2, and Q3. Let us calculate the potential energy of this system. So for that we will write the position vectors R1, R2, R3, and the difference vector, that is displacement vectors R31, R21, R32, that is between the charges. Now we have to find out what is the potential energy of this three charge system. So there are three steps involved in order to configure this system. First we have to bring charge Q1 from infinity to point A. Then we have to bring charge Q2 from infinity to B. Then we have to bring charge Q3 from infinity to B. While in the first step, you can see that since there are no charges at initially, the potential at point A is 0. Therefore, no work is to be done to bring the charge Q1 from infinity to B, A. But in case of charge Q2, when you are bringing charge Q2, there is a potential at point B due to Q1 charge. So we have to do some work. Similarly, when you are bringing the charge Q3 from infinity to C, there are two potential present at C. So you have to calculate the total potential and then you have to multiply by the charge Q3. Then you have to add all these three work done. You will get the total work done, and that is simply equal to electrostatic potential energy of this system. So let us do step by step. In the first case, work done in carrying charge Q1 from infinity to A can be written as WA is equal to 0. Now we have to calculate the work done in carrying charge Q2 from infinity to B. So let us see, is there any potential present at point B now? Yes, first we brought the charge Q1 to point A. Due to the presence of this charge, there is a potential at point B. Since this distance is R21, you can write the potential at B due to Q1 is nothing but VB is equal to 1 by 4 pi epsilon naught Q1 by R. So you are bringing a charge Q2 to potential VB. Therefore, the work done will be Q into VB, the potential into charge, and you will get WB is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Similarly, while bringing the charge Q3 to the point C, there are two potentials present. One is due to charge Q1, another one is due to charge Q2. Therefore, the total potential at point C is the sum of the potential due to charge Q1 and the potential due to Q2. So let us first calculate the potential present at point C. So you can write VQ1 plus VQ2. So you'll get 1 by 4 pi epsilon naught Q1 by R13 plus 1 by 4 pi epsilon naught Q2 by R23. This is the total potential. So what will be the total work done? Total potential VC into charge you are bringing is Q3. So VC into Q3, that can be written as 1 by 4 pi epsilon naught Q1 by R13 plus 1 by 4 pi epsilon naught Q2 by R23. So here we have three work done. First work done to bring charge Q1. Next work done to bring charge Q2. Next work done to bring the charge Q3. So the total work done, you can add equation 1 plus equation 2 plus equation 3. You will get the total work done. So the total work done, WA plus WB plus WC, that is given by 1 by 4 pi epsilon naught Q1 by R12 plus 1 by 4 pi epsilon naught Q1 by R13 plus 1 by 4 pi epsilon naught Q2 by R23. Therefore, you can write the total potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R32. This is the expression for the total energy of the three charge system. Now let us generalize the expression for electrostatic potential energy for an n charge system. So first step, we have done the electrostatic potential energy of two charge system and we got this value 1 by 4 pi epsilon naught Q1 Q2 by R12. Electrostatic potential energy of three charge system, U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R31 plus Q2 Q3 by R32. So for an n-charge system, we can write in terms of summation as U is equal to 1 by 2 into 1 by 4 pi epsilon naught, I is equal to 1 to n, summation j is equal to 1 to n, where I not equal to j, qi qj divided by rj minus ri. The next important configuration we are going to calculate or we are going to find is the potential energy of a dipole which is kept in a uniform electric field. So here is the diagram. You can see that we have a dipole of charge minus q and plus q separated by a distance 2a. So when it is kept in a uniform electric field E, both the charges experience force. Plus q experiences F plus q in this direction and minus q experiences F minus q in this direction. So you can see that the magnitudes of charge q into E are same for both charges, but the direction of the forces are different. So you can write the net force acting on the potential on the dipole as 0 minus QE plus QE. We know that these two forces constitute a couple because they are equal in magnitude, opposite in direction, and their lines of actions are different. Therefore, they constitute a torque or couple, and it gives rise to a torque. As a result, the dipole rotates. So here the motion of the dipole is nothing but rotational motion, and the torque is given by force into perpendicular distance. So magnitude of force of any one force, that is QE into this perpendicular distance, we have already done, is that 2a sin theta. So you have Q into 2a can be written as P, therefore P into E into sin theta. Now let's calculate a small work done to rotate the dipole by a small angle d theta. So from the expression we have dW is equal to tau into d theta. Let's substitute the value for tau, that is Pe sin theta into d theta. Now we are going to rotate, we are going to calculate the total work done to rotate this dipole from angle theta 1 to angle theta 2. For that you have to use integration. So you'll get W, total work done, is equal to integral dW is equal to integral theta 1 theta 2 theta 1 to theta 2 Pe sin theta d theta. Since for a given dipole P is constant, E, uniform electric field E, is also constant, so you can take P and E outside the integration and you will be left with P into integral sin theta d theta. What is integral sin theta d theta? You know that it is minus cos theta. So you will get Pe into minus cos theta from theta 1 to theta 2. So let us avoid this minus sign inside this bracket by interchanging the lower limit and upper limit. So lower limit theta 1 will become upper limit, that is theta 1. Instead of writing minus cos theta theta 1 to theta 2, we will write cos theta theta 2 to theta 1. Now apply the upper limit minus lower limit. You will get Pe into cos theta 1 minus cos theta 2. So you will get the work done to rotate the dipole from an angle theta 1 to theta 2 is given by Pe cos theta 1 minus cos theta 2. This work done will be stored as the potential energy. Therefore, U of a dipole which is kept in a uniform electric field is given by P into E into cos theta 1 minus cos theta 2. So as a general case, we will imagine that the dipole is initially perpendicular to the electric field. So we can take theta 1 is equal to 90 degree. So instead of using theta 2, we can use the symbol theta only. So the term for potential energy U is equal to Pe into cos theta 1 minus cos theta 2. In that theta 1 becomes 90 degree and we know that cos 90 is 0. Therefore inside we have minus cos theta 2 or minus cos theta. So we can write it as Pe into minus cos theta. This can be written as U is equal to minus Pe cos theta. You know that P is the magnitude of the dipole moment vector and E is the magnitude of the electric field intensity vector. Therefore, in vector form, we can write the potential energy of a dipole which is kept in a uniform electric field to be U is equal to minus P dot E. Now let's consider some special cases. You know that when theta is equal to 0, theta is equal to 90 degree and theta is equal to 180 degree. In the first case, when theta is equal to 0, you know that cos 0 is 1 and the potential energy becomes minus Pe. This is the minimum potential energy. Therefore, it is the most stable position for the electric dipole. And the next case, we have theta is equal to 90 degree. In that cos theta becomes 0. So the whole term, the potential energy becomes 0. In the next case, when theta is equal to 180 degree, cos 180 becomes minus 1. So minus into minus becomes plus. So we have potential energy is equal to PE. That is the maximum value, and that position is known as unstable equilibrium. These are some of the special cases. So in today's class, we have discussed potential energy and we have derived the expression for potential energy for different configurations of charges. First, we have seen that the potential energy of two charge system is given by 1 by 4 pi epsilon naught Q1 Q2 by R12. For three charge system, we will have this expression, and generalized expression for n charge system can be written like this. And the most important one, the electrostatic potential energy of a dipole in a uniform electric field, we have seen that the expression for potential energy is U is equal to minus P dot E. Also, we have seen the special cases corresponding to theta is equal to 0 degree, theta is equal to 90 degree, and theta is equal to 190 degree. This is for today's class. Thank you.